Welcome to the meeting of the Rotary Club of Silicon Valley. The theme of our club is innovation, entrepreneurship, and education. And we use technological advances within our meetings in our club to operate our club. Now, this week's meeting, we have a very special guest, and this is Dr. Jessica Wade from England, and she has a very different topic, and that is handedness and the future of electronics. And she is in the area of physics, and she has quite a reputation internationally, and which she is going to tell us all about in terms of what she does. And take it away, Jessica.
Okay, thank you so much for having me. I shall now share my screen and see what happens. Let's see. Ooh, that's quite cool. Share that. Got about 50 screens open. Let me see now. Yeah. Can you see that?
Yes, no problem.
Okay, great. So thank you so much for inviting me to do this. It's really funny doing it on a Sunday evening. So my name is Jess and I work at Imperial College London, which is in London, and it's in South Kensington if you've ever been there, and to the Science Museum. It's right next to the Science Museum. And I work in something called the Centre for Plastic Electronics, where we're making new electronic devices out of carbon-based materials. And the front of this slide is the kind of devices that I try to make. So I try and make light-emitting diodes, and we try and control their structure by looking for things in nature that already have these kind of structures. So I'll just give you a really brief outline of what I'm going to talk about tonight, this evening, lunchtime for you, sorry. So I'm going to tell you first about what organic semiconductors are and how we're using them, a bit about the kind of devices that we can make, then about chirality, because this is the most exciting thing that I've discovered during this stage of my research, and what we're doing to use this in devices, and then other applications that we could go into, and a bit of my work in diversity, because that's how I got this invitation, and it's really exciting. So I hope that you're familiar with inorganic semiconductors. I think you should be, given the introduction that everyone's into innovation and entrepreneurship. But inorganic semiconductors are things like silicon, and they're halfway between a metal and an insulator. So sometimes they conduct and sometimes they don't conduct. And silicon's really great for a lot of things. It's really great for making solar panels out of, light-emitting diodes out of, and transistors out of. But it's really expensive to process because the bonds between silicon atoms in a crystal are really, really strong. So they're really, really tightly packed and strong. So we have to take them to really high temperatures and pressures to process them. And it means we can never put it on a flexible substrate because we'd never be able to print it on that because we'd melt the substrate. Instead, and I hope this isn't too terrifying, we're using carbon-based materials. So here, if you remember chemistry, if you've done it recently, these are a bunch of polymers. So all of the lines on here are carbon bonds, the double lines are double carbon bonds, and the square bracket means that we repeat that unit lots and lots of times. So we've got a polymer, a repeat unit of tiny little segments called monomers. We're particularly interested in some of them. These are some of the kind of famous ones. They have their long, hideous kind of chemical name and then this short acronym that we give them. But these are really exciting because they have a special kind of carbon bonding that means they actually semiconduct. So most of the time we think plastics don't conduct. These are polymers and plastics too, but this carbon bonding means they semiconduct. If you remember this structure, this is benzene, and this is the first one that they saw this kind of bonding in. The bonds are much, much weaker than silicon. Silicon's strongly bonded, remember. Here the bonds are much weaker. So we can dissolve them. We can dissolve them in solvents like acetone, which is nail varnish remover. And we can dissolve them at really low temperatures. So we can print them at really low temperatures, and we can actually print them onto plastics. We can also control everything about them with their chemistry. So we can determine the color that they emit or the color that they absorb by putting in different elements or different structures. So it's really, really cool. And we can print all different kinds of devices. Some examples of recent ones, there was just a record efficiency for a solar cell last week, which is 17.5%, 17.3%. So this is a fully flexible solar cell, solar panel printed from these materials onto a plastic. And it's got a really, really high efficiency. This is getting near to where silicon is. This is super exciting times for organics. LG are kind of world leaders in using these in display technologies. So these kind of fully flexible television displays or mobile phone displays are less than 1 millimeter thick, and you can get them massive. You can print out 88-inch ones and have 8K resolution, which is absolutely ridiculous. That's more than you'd ever need. The things that I'm really excited about at the moment are how we can apply them in biology as well. So what's really cool about these materials is they don't just transport normal charges, so they don't just carry electrons and holes and things like that, but they can also transport ions. And as you may know, I definitely didn't know until recently, a lot of kind of transfer within the human body relies on ion transfer. And there's a really cool group at the moment. There's one in America and one in the UK using it to detect and treat epilepsy. So when you have epilepsy, you get these neural spikes, really big increases in neural activity, and it's basically like an electronic spike. And what these organic materials can do is they can sense when these spikes are happening. They can pick up really, really sensitive when these things are going on, and then push out a neurotransmitter, so push out a treatment through a pump. So it's a combination of a sensor and a pump, and you have both implanted into your brain. And because they're carbon-based, they're biocompatible, so they're much, much safer than using conventional electronics. So what's happening in organic light-emitting diodes? What are we using here? Well, LG have started making them, I've told you that, and they look really, really great. They're absolutely beautiful. The colors are incredible, the resolution's great, they're really fast response times, they're really, really thin, everything's excellent. But actually what happens is they emit, put in loads of animations to try and explain it. So to be able to watch these televisions in your home, because of all the light behind us, if you can imagine now you've got loads of bright lights behind you, if you want to have the screen there, you have to have a filter in there to block out some of that background light. So you don't want glare when you're watching your TV. So we actually put a circularly polarizing filter in front of the television so that when background light, the stuff we don't want, comes through that filter, it gets turned into left-handed light. So this is light that's got an amplitude of the wave spinning in one direction, hits off the back electrode, which is shiny, inverts that circular polarization, and then can't get out. So we don't have any problems with glare at the moment if you have an organic light-emitting diode TV, which is great, but it means that most of the unpolarized light that's going out of the pixels in the screen never leaves the screen. So you lose about 50%. What we're trying to do is make that light coming out circularly polarized so it just sneaks through that filter and you get no loss. So if we do this, and if we can control this using the structures that we make in those films, then we could have much, much more efficient displays. And how we're doing it is by using molecular chirality. And this is so fascinating to me. So chirality was first discovered by Pasteur in 1848. It's basically, you've got a chemical structure with identical molecular structures. So you've got exactly the same elements. They're arranged exactly the same way in space, but they have non-superimposable mirror images of each other. It's like your left and right hand. If you remember the thalidomide scandal, it was that was the cause of that. You had these two drugs, you had left and right-handed versions. The coolest example I can think of is the stuff that gives the smell of spearmint in caraway is actually an identical molecular structure, but one is left-handed and one is right-handed. And we can look to nature where they're using these things really exquisitely. The first one I read about recently is this mantis shrimp. So this mantis shrimp has detectors in its eyes so it can detect circularly polarized light. It's this R4 photoreceptor, which basically acts to twist the light. So it's a quarter wave plate, if you remember your physics. But this thing can detect whether light is left or right-handed. And in its shell, it reflects left and right-handed light, especially when it's defensive. So these mantis shrimps are communicating with each other using circularly polarized light, which is so clever because we don't have that functionality. We can't differentiate that with our eyes. Most invertebrates, most animals can't. So they're communicating with each other in the way only they know how to interpret. The other one are these beetles, these beautiful jewel beetles. I don't know if any of you have ever seen them. They're bright, bright green. And the structure within their shell is this polymer called chitin. So this long chain of molecules called chitin. And the molecules stack up, the polymers stack up in a twisted stack so that when light reflects from the top of that white light, it reflects back and is firstly this beautiful green, but is secondly left-handedly circularly polarized. So if you look at it through 3D cinema glasses, in one eye you have this really bright, beautiful green beetle, and in the other one you have this really dark black beetle. And it's just so cool. Like, we're only just discovering this now. The Mantis shrimp paper was in 2016. This beetle paper was in about 2015, also from Imperial. So what we're trying to do is blend together this kind of spaghetti-like polymer. So this polymer called F8BT, it's really well studied for light-emitting material applications. It's also liquid crystalline, which is quite exciting for us because it means if we heat it up, we can access all of these different packing structures. And we're blending it with this tiny little spirally twisted molecule, which is called a helicene, but it's basically a connection of lots of benzene rings that is connected in such a way it can't lie flat, so it's twisted, and that doesn't emit light. We only put a tiny amount of that in. We put about 10%. So we mix these two things together and we form these light emitting layers, and we put them in our devices, and we can actually get really, really beautiful circularly polarized light out. They're also very good at detecting circularly polarized light. So the kind of applications that we're looking at are either in these light emitting diodes, which is the kind of primary thing, but also whether we can use them in photodetectors to detect circularly polarized light, as pressure sensors. So as you can imagine from this structure, if you squish it, you change the pitch of that kind of stack. So we could use them to detect different pressures. The thing people really want, there's huge money if we could use these in biological sensors, particularly for pharmaceuticals, because sometimes one component of a drug is active and the other isn't. So you'll have a left-handed component that is and a right-handed that isn't. And then recent huge excitement, particularly from Israel, is to use them in kind of spintronic applications, which is electronics where we're using their electron spin as well as the fact that they can carry charge. So huge number of things that we can explore, and it is really, really exciting areas to be in. I think when I started this postdoc last year, everyone was like, oh, don't do it. We don't know whether the materials are good enough. And now just about every group that I've started speaking to is trying to use chiral materials in some way. And it's this beautiful kind of intersection of chemistry, because that's great. The synthesis is really fun. Biology, because of all of these biological structures are inherently chiral. DNA is chiral, proteins are chiral. And also physics, because the actual optics and the engineering of these things is really fascinating. Okay, the other side of my world is a lot of work about diversity. So I just Googled this today to make sure I wasn't wrong. But if you Google list of famous physicists and list of famous engineers, basically everyone that comes up is a man, they're all white men. And this isn't the physics that I know, and this isn't the physics that I see around me every day, and when I go to conferences and when I work with people in the lab. And it's getting a bit worse than just Googling. A CEO, a woman CEO of one of the big kind of tech companies, typed in, she's the CEO to her iPhone. And the kind of, the suggestion was this sort of white man with blonde hair. So that's the predictive, that's the iPhone saying this is what it is. So it's already on the internet, and then it's creeping into the kind of software that we create. So this frustrates me. This frustrates me a lot. A lot of the time during my PhD, I was going around speaking to lots of girls, trying to get girls more excited about science, and none of it was really working. And I think I became really frustrated with what was going on. So what we do at the moment about girls in physics is we assume that they're not really interested. So we think, oh yeah, we've got to inspire them. Let's go out, let's inspire them. Let's put on this big show. We blame them. We keep telling them they're wrong and physics is really amazing. And come on, it would be so much greater if you come over here. We might make some posters. We rename things. We open buildings. In the UK and in America, I know you do because I've come to visit recently, we spend millions of pounds on these kind of education initiatives that have absolutely no evidence behind them. So it will be a bunch of corporate people, it will be really big engineering firms who think, oh, diversity is awful, let's make a £300,000 video and that will convince everyone that they need to study physics. And it's incredibly superficial. Or we get people to go in, and I did this as a PhD student, go in to do talks in schools. They might stay for an hour, they might stay for a lunchtime, and assume that that will have a long-lasting impact on what young girls choose. And I think that's naive. I think that young people are much more sophisticated than that, and they forget about you at the end of the day or at the end of the week. What we don't do is we don't try and challenge all the biases that are already in society, particularly with parents and teachers. So these are the people who really push these things out, these misconceptions about what men and women can and can't do. We don't pay science teachers properly, so we have a really hard time, especially in the UK. I think that only 1/3 of our physics teachers have an A-level, so have a high school qualification in physics, and the majority of them leave after 5 years. That's awful. And we don't champion the women who are already there. So there are huge amounts of women in science and technology that we just don't shout about. Luckily, the Institute of Physics have done a bunch of research for the past 20 years, and I've put it all here. Actually, I haven't put it all here. They've put it all here, but you should go here and read about it if you want to. Particularly, they found that the only way you can change any of this is to have the whole school on board with it. The schools that have the fewest numbers of girls in physics also have the fewest number of boys in the arts and psychology. So stereotyping is impacting everyone. And we need to start getting a lot better at giving careers advice and to get young people on board with challenging it. Then I read this incredible book called Inferior, which is by Angela Saini, who's an engineer turned science writer. And it's basically a look at the origin of these stereotypes. Where did they come from? What are the causes of them? Is there any science behind them? If there is it true? And why are we still propagating them in a society where men and women should be equal? And it basically all starts with Darwin. Darwin was very keen on the fact that women were intellectually inferior to men. Apparently we're morally superior, but intellectually inferior. In The Descent of Man, he says men have higher eminence in everything that they try and do, whether it's kind of poetry or science or geography, anything. And this is crazy because the world that Darwin was looking at was a very biased one. So at the time, women couldn't go to university. They couldn't graduate from Harvard until 1948. They couldn't graduate from Cambridge until 1948. They couldn't even be fellows of the Royal Society until 1946. So when Darwin was knocking around, yes, we were inferior because we couldn't access any of these things. It's only this year that's a centenary of women over 30 being able to vote. And not only is this not fair because it's not just, it's not fair because we have worse outcomes because of it. So it was when they first launched the seatbelt disproportionately killed women and small children because it was only tested by a team of men. So they actually made the seatbelt, put it in cars, and then women and small children died. And they thought, why has this gone on? And they realized because their design team was all men. It was only in 2005 that they had to start testing medicine on women because they were killing women more often than men. So all medicine that we take gets tested on men because they don't change over the course of the month. And apparently men may or may not be pregnant. So for ages, they got away by not testing them on women, which seems insane, 2005. And as a result of this incredible book, Inferior, I met a great researcher called Amy Parrish. And Amy Parrish was in San Diego Zoo, so near to you in California, and she was studying bonobos. And bonobos are fascinating monkeys. They're actually our closest living relative, very similar to chimps. But instead of the kind of patriarchal society we know chimps in, while Amy was observing these things, she realized that it was a matriarchal society. So actually women were in charge, and these women were super aggressive and just hitting all the men bonobos. And she went all over the world studying these bonobos. And in every zoo she went to, the zookeeper said, oh no, it's just our men. They're really weak men. We've got really weird men. And she was like, no, this is happening everywhere. And she found this out in 1990. Like, imagine, that's so recent. We've lost all of these stories. Something that I do a lot is edit Wikipedia, and that's certainly why I got invited here today. So Wikipedia is an insanely powerful website, fifth most accessed website in the world. There was just this article in The Guardian today saying that in the current crazy world we live in, it's the only form of truth. So it's the only thing where we've got people policing each other, checking each other, and contributing to this massive wealth of global knowledge. But Wikipedia itself is incredibly biased. And if you look at the biographies, oh no, my slide hasn't worked. Let's see if I can get rid of that. Oh, well, if you look at the biographies on Wikipedia, only 17% of them on English Wikipedia are about women. So 17% of the biographies on English-speaking Wikipedia are about women. And this is ridiculous because we're 50% of the population. And even if we may not be represented in science, we're certainly represented in different fields. And I think this is crazy. And it's basically because the majority of editors are men. So I started editing Wikipedia. At the beginning of this year, I started contributing more and more pages to Wikipedia, particularly about women in science, because that's what I'm familiar with. And I started to have these kind of wikithons. I got loads of students into Imperial and got them to start editing Wikipedia, which is really great at them learning about bias, but also really great at them learning how to write an impartial biography of someone and cite sources and know things like there are some people whose pages you can't edit. And I'll let you think about who they might be because it's very hard for people to be impartial about them. And since then, I made like 300 different pages, which is so cool. And they've been great. And people have looked at them. Today, they had, as a result of the kind of Guardian article that came out, a woman composer had a whole session on women composers and got loads of people together in the South Bank Centre in London, which is a huge music hall, and got them all mass editing, which is so cool. So that was the result of that. And a boy that did physics with me estimated the number of people who've been reading these pages as I've been making them. He used the kind of wiki page view statistics. And since the beginning of this year, it's going up to like more than 200,000, which is crazy, right? Like I just edit these things by night. And so someone wrote a Guardian article, and in the past month, I've been in like every news thing in the entire world. Even China emailed me to ask me to do this. So it's been absolutely massive. And off the back of that, I thought I'm going to crowdfund to get this book into every school in the UK. So I set up a crowdfunding campaign thinking we could get it into maybe 200 schools. And in 12 days, we raised enough money to get a copy of this book into every single state school in the country. So every single free school in the country, which is great. And then I got this email on Sunday. No, not on Sunday, on Friday. I'll let you read it because it's so beautiful. A-level is our high school equivalent. So lovely. So when I was doing this in crowdfunding, I was like, oh my gosh, actually, this is quite a sophisticated group. And I don't know if quite a sophisticated and grown up book. And I don't know if everyone will be able to interpret it. But this is a kind of 16-year-old girl who's read it. And I just think that's so powerful and great. So now we're going to raise it. On Tuesday, we're going to launch one for New York schools. And then after that, we'll do California. You're just a tiny bit bigger than New York. So I wanted to show we could do it in New York first. So yeah, I think I should stop talking because I have to start taking questions. But I wrote down a list of things that I think everyone can do. I think everyone can start to challenge bias. Obviously, everyone can edit Wikipedia. I think that particularly when you're hosting a conference or organizing people to speak, you have to spend a bit longer to find women, but you can always find women. I was invited to talk at a material science conference recently in Paris in December, and I was like, yeah, of course I'll go to Paris in December, don't worry. And then I looked at the list of people speaking, and it was 2 women out of 45, and I was like, this is ridiculous. And so I just invited 3 more, and so now we're going way more across than we were before. Think about things when you cite. This is particularly a problem in academia, that men only cite other men and also cite themselves more often, which is not a very nice thing. Think about the language you use on people's references. Amplify, mentor, and champion, and nominate people. And then these are some links that you can find other things on. So now, and I can send you all of these slides too. Oh no, but you get the thing recorded, so that's perfect. Now I'm going to stop sharing so I can see you and answer some questions. Hello.
Thank you very, very much for a very interesting discussion, Jessica.
I'm sorry I went on for too long.
We'll open it up now for questions. And Farine.
Jessica, first off, you are absolutely amazing. So I don't know if you noticed, but I was like just snapping the whole time.
I know, I was like, I must be doing something right. I hope that's not, I can't hear.
No, like I was just snapping an affirmation of everything you were saying. So I'm a biologist by training. I just finished my master's in reproductive biology, and right now I'm doing pre-med classes because I want to become a doctor. And everything you're saying is absolutely 100% correct. You know, as a woman in science, absolutely. I have tried to challenge so many systems of oppression within, you know, this field of science that I get it. Like, I so get it. And everything you said was just phenomenal. But first off, I just want to affirm all of your research. And I think that's amazing. I am right now, because again, I'm a biologist. So, you know, we're looking right now at chirality of different molecules and proteins. And I mean, what you're saying is absolutely awesome. And really quick, so I lived in Japan for 3 years doing my master's, and one professor that I met actually doing something really similar to what you're talking about. And like, I just pulled up his article that he wrote, and really quickly, it's about the antibacterial properties of Si nanopillar array fabricated using metal-assisted etching. So basically mimicking a cicada wing. So yeah. So, you know, kind of using biology and a biological system to kind of create like a human-made fabric, right? So yeah, so what you were kind of saying, super similar. Yeah. So I was like, oh, I know this.
You should send me the link. I always want to find cool new people who understand a bit more. The challenge in this area is because it's kind of been left to biologists for so long, the characterization techniques that we'd rely on in physics aren't quite up to what they should be yet. Absolutely. So it's really interesting trying to interpret things when everyone, you can imagine, some people call it chiral, some people call it circular polarized, some people call it helical, some people call it
antimers.
Yeah. Right? So I think that just getting people together to talk about it. It's so fascinating when you start exploring.
I agree. Absolutely. I absolutely agree. And so sorry for the non-scientists in the club, in the group. What you said about, again, diversity and bias, it really, struck a lot with me. So again, I was in Japan, and a majority of the professors that I had, so I had over 90 different lectures in my classes, and only 4 of those professors were women.
And that's inferiority.
It hurt so much to see that, and again, reading my biology textbook, all men, right? And it really makes me think, if women were given the tools to do the same things, what else would we have discovered, And that's partly one of the reasons why, like, I want to keep fighting, and, keep doing science, keep doing research, keep continuing this path, because I get it. Oh, and I want to edit Wikipedia articles with you. Absolutely.
Sure.
And I definitely will read the book. Okay, that's all. Okay, I'm done.
Okay, so I have a question.
Julia, go ahead.
So I thoroughly enjoyed your talk. I'm really the non-scientist among us, although I do have an interest in science generally. Here in Silicon Valley, we do have a lot of women now, young women, who are software engineers. And, and so my question is that considered a science, software engineering? I mean, I think
it is 100%.
Pardon me?
100% it is. So we have the same, so at Imperial, we put computer science into engineering, but obviously the same challenges face women in science and in engineering. And I think that the attractiveness of Silicon Valley as a place to work means you kind of act like a magnet to pull all of the really great women, because they know they're going to go there, have the sun, and have a really high salary. So I think that whilst it may all look okay in Silicon Valley, there are parts where it's much, much worse. And then even though they're there at the beginning, you still have things like that horrible Google memo coming out of Google, unsurprisingly. And then there was a Facebook version about 2 weeks ago. So I think that even though there's disproportionately more women in Silicon Valley than probably the rest of America, you still have these biases with the people that they work with. And in some ways, that's even more toxic, because they're there and they see them every day.
Yes. There's no question about that. And I mean, I have among my clients women who have done very well in their companies, and then 5 or 6 years into their employment have discovered that they're being underpaid for the same position by 30-40% compared to a man who has the same, or perhaps even less, a bit capability than she does. And so it's going to be a long time before we work those biases out of the system. But I did notice in one of your links that it was bringing bees to flowers or something like that. Is that what?
No, okay, that was, yeah, I agree.
That we're all interested in here in California.
I agree on the payment thing. That's something that I think we all just need to be much, much more transparent. A friend of mine in astrophysics just got a really prestigious fellowship, and then found out that she's automatically been paid like 4 levels below the men who've got the same fellowship. So it's crazy. And I think that women also disproportionately take on a lot of tasks that may not result you getting in promoted. So she does a huge amount for the university, way beyond the call of her own research. She goes out, she talks, she's running a huge nationwide policy campaign to try and end staff student sexual harassment. And that's not something that you may get an increase with for doing an astrophysics fellowship. The other thing, the link in that article is the link in my talk is just to this really beautiful article that was in Physics World about how we can control nanostructures and how we can mimic ones from nature. So that it's kind of all the beautiful examples that we have, like butterflies and peacock wings, where the color doesn't come from a pigment, it comes from the way that light is reflected from the surface. And I just think this is so cool. Like, it's so hard, apparently, for nature to make the color blue. So the majority of things that we see that are blue are just layers of different structures on top, so that when light reflects, we see blue. And we're kind of just catching up with that. So we're kind of just working out now how we can structure things to get that. So that was that link. But it's a really fascinating read.
I'll go read it.
Yes, Rustin.
So cool to have you talking to us. You'll find a lot of welcoming ears to the social message for sure. We highlight great stories about women in science in our club. Just 2 weeks ago, Gitanjali Rao, the high school student, our middle school student who discovered a better way to test for lead and water. You know, so that's near and dear to our hearts. I want to get back to the organic semiconductors idea, though. So, you know, talking about the work you've done, if what we're creating is coming out of an organic process, is there a danger that that is creating any kind of environmental concern with how these products, whether it's how they're built or how they decompose or anything like that? Is that a concern as a part of the work you're doing?
So great question. The majority of materials that we use are actually quite safe to make. The synthesis is all right. And the layers that we use are incredibly thin. So that the active layer of a plastic, which is obviously the thing that we're trying to get rid of in the environment, the active layer is about 100 nanometers. So this is really, really thin layer compared to silicon-based technologies. So actually what we're using is much more environmentally friendly. And now you can develop plastics that also biodegrade. So these aren't those ones yet, but they're ones where we're using such a tiny amount of it, it's not even really a concern. And if we can increase the efficiency of them and the stability of them, and then get them processed massively on huge areas. I mean, the plan with the solar panels is that we print them using kind of newspaper printing techniques. So you print them roll to roll, and then you can just roll them out across deserts. And there you'd be harnessing so much energy, it would kind of overcome the fact that you've used this 100 nanometer thick piece of plastic. The difficult ones are the kind of rising star in this field at the moment is something you may have heard of called a perovskite. It's a crystal structure that's kind of a mixture of an organic and an inorganic material. And it will almost certainly win this professor from Oxford a Nobel Prize. Like, he's incredible for finding it. They're insanely efficient solar cells. So the increase in efficiency in about the last 3 years since they've been researching them has been much, much more dramatic than anything inorganic or anything organic. But they contain lead and occasionally leak chlorine gas. So the scientists who are researching them have to have poison tests once a month, and all the tables in their labs go yellow. So everything about it is like, no, we should not be doing it. But it's so efficient that people are now trying to find alternatives to that, and also to keep testing them. Because as you know, in academia, you just want to publish a high number and you don't really care what happens to all the master students and the PhD students who are doing the research. So that's the frightening one. That's the one where it's so impressive that things are pushing much faster than they should be given what they're made of.
Wow. Okay. So many cool topics coming from that. But I also wanted to make sure I understood something else that you talked about. When we talk about being able to create these organic semiconductors, and that these become a part of how displays are developed with companies like LG, is it that the efficiency of the system allows for the higher resolution of the screens? Am I characterizing that properly? Yeah.
So we don't, the efficiency isn't actually the thing. We can get incredibly luminous materials. So we can get materials that emit very, very bright light. We can control the color that they emit very carefully. So instead, at the moment, you almost have a white light and then in front of it a filter. So there you get a few different colors, and you change which colors you light up at a different time to represent a different color that we then see. Because each of these pixels is emitting its own light of a particular color, you can tune the resolution that you get very well. But they can also be absolutely tiny, so you can control their size really precisely by using carbon-based materials. They also have much faster response times, so we can turn them on and off much, much better. And they can get, if you've ever seen one, I don't know if you've ever seen an organic light emitting display, they're absolutely beautiful. Like, the black is so black, you can't really imagine the kind of richness of color that you get. So once you see one, it's very hard to go back to the kind of conventional way that it was before. I remember the Natural History Museum had a whole exhibition on color, and it was all on the way that animals see. It was just incredible. And LG had sponsored it. So at the end, they had this absolutely massive LG screen, and it was just this kind of, yeah, it's the depth of color that you get, which is so incredible, because you have that really, really black and that really, really blue that you really don't get in any other way.
Wow, wonderful stuff. Thank you so much.
Okay, great.
Thank you very much, Jessica, for your presentation. we're running some a little bit late here, so what I'm going to say to you is thank you very, very much. It was extremely interesting. And I think all of our club members will really enjoy this presentation. Now, at the bottom of our screen, at the end of the meeting, there is a comment section for anybody who would like to make comments on the presentation of Jessica. And please do that. For those people who are guests, please fill out the attendance record and also members. For the guests, if you put in your correct email address, then what will happen is you will get an email back from our club so that you can take the receipt for attending this meeting to your club secretary. Jessica, I want to thank you again very, very much for your presentation. And as is customary within our club, I'm going to give you the opportunity to have the last word. So please go ahead and give us your last thought for the day.
Okay, my last thought for the day is whatever industry you work in, please champion all of the underrepresented groups in it and help us up because we really need an opportunity to shine. Thank you.